Now we're going to work on some of the applications of gas laws. Two of the applications that we have very commonly are density and molecular weight, okay, of gas laws. So these are the problems you're going to do. So the first one that we'll work on is calculate the density of methane gas, which is CH4, in grams per liters at 25 degrees Celsius and 0.978 atmospheres. It's specified here that your units are going to be gram per liters, okay, because the volume of gases is very large. Otherwise, usually in chapter 1 we learned that we actually work in grams per milliliters, okay, but just a minor thing, okay, just to point out. But anyway, this is going to be grams per liter. So our equation for density is molar mass pressure over RT, okay, and that's an equation that I will also give you in the exam. So you just need to know how to work it. All right. So density is molar mass times pressure, and then R, and then T. Okay, divided by the temperature. So you want to make sure that your temperature is in the right units. So 25 degrees Celsius plus 273. That never ends. Okay. And so then 298 K, and the pressure is already in atmosphere, so we are fine. And then we need to find the molar mass of CH4. And molar mass of CH4 is 16.04 grams per mole. Okay, so that's what we need. So now just plug in all the numbers. So molar mass is 16.04 grams per mole times the pressure, which is 0.978 atmosphere, and this is divided by R, which is 0.0821, and liters atmosphere, and remember this is divided by mole Kelvin, and technically if it's divided twice by the top number then it actually goes up anyhow. And then the temperature is 298 Kelvin. Okay, so the first thing I want to do is go ahead and cross out my units. And so Kelvin goes here, and moles is gone, atmosphere is gone, and I'm left with grams over liters, which is exactly what I'm looking for because that's the density. Okay, and so once we do the calculation for this one, our answer should be 0.641 grams per liter of methane. Okay, it's simple enough. Plug in all the numbers in the equation. That's the nicest thing about gas laws, okay, is that once you know what the equation to use, then you can easily work on the problem. Okay, let's go on to the next one now, which is calculate the molecular mass. Okay, now the molecular mass is the grams per mole of a liquid that when vaporized at 100 degrees centigrade and 755 torr yields 185 milliliters of vapor that has a mass of 0.523 grams. Now in this case you probably noticed that we have a lot more data given to us. Okay, the equation that we are going to use here is a little bit different than what we had for density, because this is the one for molar mass, and the way to calculate molar mass is this equation, okay, where we have MRT over PV. Okay, and M here is the mass, the capital M is molar mass, and M here is mass, the small m here is mass. All the other numbers, all the other letters you already know. R is gas constant, T is temperature, pressure, and then volume. Okay, so everything else is fine. Now what we need to make sure is that our units are correct. Remember, molar mass is going to be grams per mole. Okay, that's the units we are looking for. Okay, so then let's get started. Our temperature is 100 degrees Celsius, which is then converted to Kelvin, okay, to 73, which is 373 Kelvin. Then pressure we have to convert to atmosphere, so 755 torr times 1 over 760 torr. Okay, and this one, I will tell you in a second what that is. And this is 0.9934 atmospheres. Okay, volume is going to be 185 milliliters times 1 liter divided by 1,000, which is 0.185 liters. Okay, all right, I think we're ready now. So then molar mass is equal to the mass, which is 0.523 grams times R, which is 0.0821 liters, atmosphere, mole, Kelvin. Temperature is 373 Kelvin. Okay, and then pressure and volume are the denominators. So the pressure is 0.9934 atmosphere and the volume is 0.185 liters. Okay, let's cross out the units. Atmosphere, and then let's see, Kelvin is gone, liters is gone, and we are left with grams per mole. Okay, so we're on the right track over here. And the answer for this one after the calculation is 87.1 grams per mole. Okay, I know it's a little bit messy over here, there. Okay, so that's our final answer. Let's work on a third problem, and this one is, under what pressure must oxygen be maintained to have a density of 1.50 grams per liters, and I forgot to mention the temperature at 25 degrees Celsius. Okay, at least we need to have some information over here. So using our density equation, because this question deals with density, remember density is molar mass times pressure divided by gas constant and temperature. Okay, so it really does not need a whole lot of information. The question is asking us for pressure, so that's what we need to isolate out from here. So then pressure is going to be dRT divided by the molar mass. Okay, so our density is 1.50 grams per liters. R is usual 0.0821 liters, atmosphere, mole, Kelvin. Temperature is 25 plus 273, which is 298 Kelvin, and then divided by the molar mass. Okay, and the molar mass of oxygen is 16 times 2, okay, which is 32 grams per mole, so that's times 32 grams per mole. Okay, and so pressure, remember the units are going to be atmosphere, so that's what we are aiming for. So let's go ahead and cross out our units, and liters, moles, Kelvin, grams, and then grams. Okay, and we are left with atmosphere over here. So then our answer is 1.15 atmosphere, which means that the pressure of oxygen must be maintained at 1.15 at 25 degrees centigrade for it to have a density of 1.50 grams per liters. Okay, so just a little bit manipulation of the gas laws.